Okay, so what is inverse kinematics? So what I have on the screen here is a robot, and let's go ahead and pick something up. Okay, so what did I just do? I gave the robot a specific point in three-dimensional space to go to. This point was defined by an x, y, z coordinate, known as a Cartesian coordinate. Inverse kinematics is the process by which you can calculate the angles of those joints when given an end position. So let's go ahead and reset that robot, and we're going to tell him to move again. So we've reset the robot, and this time I want you guys to keep a close eye out on the angles on the left side nav there. We can see that each joint angle changed. If I were to go ahead and grab each joint and move it, we can see the effects in the simulator. So I'm going to go ahead and drag joint 2 around, joint 1, and you can see that moving. Okay, but how can I go from an X, Y, Z position in space to 6 joint angles to set the robot to? Well, to understand that, we have to first understand what a frame is. This is called a frame. A frame is basically an XYZ coordinate system that exists in a specific location and has a specific rotation. If I were to start clicking one of these directional radios, you can see that the frame rotates itself such that the blue z-axis points in the direction we tell it to. We can grab and change each rotation individually to see more clearly how the rotation affects the frame. It's important to note here that each rotation is around the new axis, not the original. These 3 consecutive rotations have a name. They're called Euler angles. If we look at each rotation individually, we can see that the rotation occurs about a specific axis. The axis that each rotation occurs on depends on what Euler angles you choose. In the case of this example, the default is XYZ, yaw, pitch, roll. I can also choose a different set of 3 rotations, ZXZ. If I do this and start to play with the individual axes, you can see how the rotations are different, but I can still achieve the same end result. If I keep it set at a negative Z and go back to the XYZ, you can see that it has 1 rotation around the Y-axis, where in the case of ZXZ, it has 2 rotations, one around the Z and the other around the X. It's important to note that there are multiple solutions to the same problem. We can see that if we change the negative 90 degree and negative 180 degree to positive values, we still get the Z pointing in the direction that we want, but the frame has a different resulting end rotation. Why is this important? Well, in order to calculate the angles of each joint in a robotic arm, you must first define a frame for each joint. Let's go back to the robot and click on the skeleton button. What we see here is what's called the Kinematics diagram for the 6-axis robotic arm. If we rotate around, we can clearly see that each joint has its own defined frame, where Z is always pointing out of it. If I were to, for example, rotate joint 2, we can see its frame rotating as well. Another observation to make here is that the rotation's following the right hand rule, where if you pretend your right thumb is the positive z-axis, the blue one, the rotation will occur in the direction of your fingers. We can start to move the arm around and see all of the frames rotate, just like the frame we saw previously. Let's go ahead and re-enable the visual robot. As you can see, beneath the arm are just a collection of frames where each frame is connected by a link. To show this more visually, I've went ahead and color-coded each link to its corresponding slider. When I go ahead and hide the robot, you can see that the length between each frame is shown here. And again, we can move the end effector around to see how they behave. So we understand that the arm is made up of joints, where each joint contains a frame, and each frame is connected to each other by a link. But what do we do with all this? Well, the answer is complex, but for the purpose of this video, I'm going to try and keep things simple. Basically, each frame is affected by its previous frame in some way. In order to define this mathematically, you can use what's called rotation matrices. What you see on the screen now should look a little familiar. This is the frame rotation that we saw previously. Currently, you can see that we have the second frame, the one with the deeper colors, rotated to the left around the z-axis. What would happen if we wanted to describe this rotation of this second frame relative to the base frame? And what I mean by that is the rotation of the frame with the deeper colors relative to the frame with the longer lines and the more opaque colors. If we take a trip down memory lane, we'll remember that in school we learned that when you have a vector, in this case we have three, the red, the green, and the blue, you have different parts that make up that vector. In a two-dimensional space, you might have a line where you have an x portion and a y portion that makes that line up. Well, in a three-dimensional space, you have an x portion, a y portion, and a z portion. Therefore, we can represent each of these lines with three numbers. On the right, you can see we have a table. For the purposes of rotation matrices, we can actually assume that the lengths of these deep colored lines, the red, the green, and the blue, are all of length 1. Knowing this, let's start to fill in some of these numbers. First thing we're going to do is we're going to draw the portion of x1 relative to x0, which makes up this red line here. The next thing we're going to do is we're going to draw a line that shows the projection of x1 on the y0 line, which is this green line shown here. Now, for the x1 on the z0, there is no portion on that, so we're going to draw a 0 in this location. Now, if we move on to y1's projection on x0, we can see we have a red line representing that. And we'll go ahead and fill that in the box here as well. Next, we need to find the y1 projection on the y0 line, which is this green line. And finally, for the y1 projection on z0, we also have a 0 because we do not have any segment of the line there. So we put a 0. And lastly, for z1, there is 0 on the x0. There is 0 projection on the y0. And finally, because z1 is in the exact same location as z0, we put a 1 here. So when you draw kinematics diagrams, you typically don't draw them the way we just did in that example, where we turn something by 25 degrees. More often than not, you'll have frames that are within 90-degree rotations of one another. So what I want to do is, before we move on and look at the robot, I want to show an example of a 90-degree rotation around the z-axis. So if we look here and we start filling in these numbers, we can see that x1 has no projection on x0, but x1 is in the exact same direction as our original y, so we put a 1 here. x1's projection on z0 is 0. y1's projection on x0 is -1. Why? Because that green line is facing the opposite of the original red line, so it's the negative of the original x0. There is a 0 projection of y1 on y0 and a 0 projection of y1 on z0. Finally, z, because we rotated around the z-axis, has no projection on x0, no projection on y0, and is in the exact same direction as the original z0, so we put a 1 here. And when you typically look at the rotation matrices in kinematics diagrams, you're going to see tables that look like this, where you see 3 1s in different locations depending on how it's been rotated. Now that we have an understanding of how rotation matrices are defined, let's go back and take a look at our kinematics diagram from our 6-axis robotic arm in the simulator. If we look at this, we can see that those frames, which should look pretty familiar at this point, are going all the way up from the bottom to the top, where each individual joint has its own frame. If we take a look and analyze just one rotation matrix from the 0 frame to the 1 frame, we can start to define some values. If we look and see the x1 projection on x0, we can see the two red lines face each other in the same direction. So that is 1. And there is 0 projections on the y0 or z0. If we look at the y1, we can see that the y1 is facing in the exact same direction as the z0. The green line of the second frame is pointing up, just like the blue line of the first frame. And if we finally look at z1's projection, we can see that z1 is pointing in the opposite direction of y0. So we put a -1 here. If we continue this pattern, we can go all the way up the entire arm and define these rotation matrices for every single frame. Okay, so now we have the rotation matrices defined for each frame in our kinematic diagram. The problem is that with this current implementation, we don't take into account the rotation of each joint when it's not 0. So basically, in its current state, all of the rotation angles of every single joint is 0. If I were to change any of those angles, let's say I took joint 2 and set it to 25 degrees, then we need to take that angle into consideration. In order to do that, we need to apply something against our currently defined rotation matrices. The way we do this is we can actually take a dot product. We can multiply the rotation matrix that we have defined by the rotation around the axis in which it rotates upon. In the case of all of our defined frames, we rotate around the z-axis. Therefore, if we take each one of our rotation matrices and multiply them by our z rotation matrix, we can have resulting rotation matrices that will allow us to get all of the rotations given a set of angles. But what is this magical z rotation matrix? How do we derive it? Well, as it turns out, we already did, kind of. Remember before in the video when I showed you guys this? This was a rotation around the z-axis, and we showed some triangles and how the different lines in the triangles corresponded to the rotation and the locations in the rotation matrix. If we just look at those triangles, we can actually replace those lines with some equations. Let's define those equations, and I'll tell you how we got there. So again, if we remember from school, the sine of some angle theta is the opposite over the hypotenuse. The cosine of that angle is the adjacent over the hypotenuse, and the tangent is equal to the opposite over adjacent. Remember, we stated before that all of the lines in our frames for these rotations have a length equal to 1. Therefore, we can actually rewrite these equations as what we see here. So the hypotenuse of all of these is equal to 1. Therefore, the sine of t is equal to opposite over 1. The cosine of t adjacent over 1. The tangent of t is the opposite over the adjacent. Or we can just say the sine of theta is the opposite, the cosine of theta is adjacent, and the tangent of theta is the opposite over the adjacent. The important thing to note here is the sine of theta and the cosine of theta. They're equal to the opposite and the adjacent. Well, let's take a look at these triangles. Well, the dashed red lines and the dashed green lines are just the sine of theta and the cosine of theta. Therefore, we can replace those in the rotation matrix with cosine of theta and sine of theta. And using the visual we have here, we can clearly see that the y1 projection on x0, which is the smaller of the two red lines, is in the negative direction. So therefore, that is why we have a negative sine of theta in that spot. Finally, with this new understanding of what a z rotation is, we can then multiply that z rotation matrix by the rotation matrix that we've defined before in our kinematics diagrams. Shown here is the first dot product multiplication of that process. We take the z rotation matrix that we just defined, we multiply it by the rotation matrix that we derived previously for the first joint, and out comes our rotation matrix that can take theta t1, which is the first angle of the first joint, as an input value. If we continue this process and we do it for all the additional rotation matrices that we would have previously defined, if we continued and done the process for each individual joints, which in this case there are 6, we end up with this. And as you can see, each one of these is color-coded. You can see they all take different angles. There are 6 joints, therefore there are 6 angles. And voila, for the first time in this video, we actually have something pretty powerful here. What we have is a method to get the final rotation of the end effector of our robotic arm. How do we do that? It's actually pretty simple. We take each of these rotation matrices, we plug in our theta angle for each one, and we dot multiply them together. So we would take the first 2 and multiply them together. We'd take the next 2 and multiply them together, and the last 2 and multiply them together. And then we could multiply the results of those all together. And finally, we'll end up with the actual end rotation of the end effector. Now, what we're actually doing here is not yet inverse kinematics, but rather forward kinematics, because we are assuming we are given 6 angles, we plug them in, and out pops the rotation. Ultimately, our goal is to get the inverse kinematics, where we give an end effector location and we can figure out what angles to set all the joints. But it's important to first understand rotation matrices, frames, and how forward kinematics work, because it's necessary to do inverse kinematics. Now we're building up a puzzle and we're actually missing a pretty important piece. We've talked a lot about the rotation matrices and the frames, but one thing we haven't talked about yet is the displacement vectors. What does that mean? Well, in layman's terms, it just means how far away is one frame from the other? How long is the link that connects the 2 joints? That becomes important when doing forward and inverse kinematics. And all it is really just an addition to the existing matrices that we have. Currently, our matrices are 3x3 matrices to represent the different rotations. If we were to add one more row and column to this, we can actually add the displacement portion of these matrices, which represent the x, y, and z Cartesian coordinate of the frame. Now, it's important to note that this x, y, z is relative to the previous frame, not the base frame. So just like when we defined our rotation matrices from frame to frame, so from frame n to n-1, we will do the same for the displacement vectors. Let's go ahead and take a look at an example. Shown on the screen are the first 2 frames from our previous kinematics diagram. What I've done here is actually offset the frames from one another in both the x, y, and z directions. This can be noted by the red, green, and blue, A, B, and C, respectively. If we were to go ahead and describe these vectors, we would just call them distances, and we would add them in the rightmost column of our updated matrice. Now please note, in order to keep the matrice the correct size, width, and height, we want it to be uniform. It's a 4x4 matrix. So it turns out what we can do is we can actually add 0, 0, 0, 1 in the last row to make this a uniform matrix. Now remember from before when we were doing the rotation matrices that we had a problem. We first defined the rotation matrix, but we didn't take into account the angle theta, which varies depending on the joint angle. The same is true here. Let's go ahead and take a look at another example. This is basically the same example we just saw, but slightly simplified. I removed displacement along the x-axis. Note how we now have a red 0 where A used to be, because when the joint angle is 0, we have no displacement across the x-axis. But the same is not true if we had an angle theta about the first frame. So let's say our first joint was rotated by an angle T1. It's best to look at this from a top-down view. If we look at the top-down view, we can see the original drawing at the top, and then when we applied an angle T1. You can see now we have a displacement in both the y direction and the x direction. Another important thing to note here is that the y displacement is no longer going to be simply b, but rather it's going to be a portion of the triangle shown here. Again, remembering that sine is opposite over hypotenuse and cosine is the adjacent over the hypotenuse, we can actually determine that these two first values are b times the cosine of t1 and b times the sine of t1. If we go back and look at the first two frames for our kinematics diagram, we can see that the second joint is just directly above the first joint. So in this case, we actually have a pretty simple matrix defined, where we have 0 displacement in the x, 0 displacement in the y, and a displacement of c in the z. So what we've defined here actually has a name. It's called a homogeneous transformation matrix. It's basically a matrix that takes into consideration both the rotation and the displacement. And it turns out, just like we could multiply all of the different rotation matrices together to get the output rotation of the last frame relative to the base frame, i.e. our end effector of our robotic arm, we can do the same thing with homogeneous transformation matrices, and we can actually take the last three values in the rightmost column to get the position in three-dimensional space of the end effector. And it turns out what we just did is forward kinematics. We used rotation matrices and displacement vectors to create homogeneous transformation matrices. We dot multiplied them all together, and the resulting matrix in the last column has our end effector location. Now in practice, we don't typically derive these homogeneous transformation matrices by hand like we did here. We actually use a process called the Dennevant-Hartenberg method. Basically, with the Dennevant-Hartenberg method, you can plug in a bunch of known values from your kinematics diagram, and out will come these homogeneous transformation matrices for you. In part 2, I'm going to go over the Dennevant-Hartenberg method and show you how you can use it to not only get your homogeneous transformation matrices, but then go the next step and actually use the stuff we've learned in this video to do the inverse kinematics. If you like this video, please like and subscribe, and I look forward to seeing you guys again in part 2, where we go more in depth on the inverse kinematics.